Hello and welcome to the third lecture on the electrical and electrochemical characterization by scanning probe microscopy techniques. So here we are going to talk about the dynamic Kelvin probe force microscopy methods, which will include first the ways to run the KPFM, so what kind of engines can be behind the KPFM measurements, and also the spectroscopies based on the top of the KPFM detection. So let's start with a very quick recap of the classical KPFM operation. So here, sort of the Kelvin probe force microscopy as proposed 30 years ago is based on this dual pass scheme. So we use a AFM probe either in contact or intermittent contact regime to determine the position of the sample surface. So in this regime, the probe is mechanically driven. Then we turn the piezo off, we lift the probe above the surface, and we retrace the surface topography while we are applying the bias to the probe. So the bias have the DC component and the AC component, and the application of the bias between the probe and the surface results in the capacitive force. So the capacitive force is generally quadratic in nature. We use the piece of electronics called the lock-in amplifier to select the first harmonic of this force, which turns out to be linear both in the driving bias and the DC bias. And then we use a feedback loop to nullify this first harmonic of the force. So it's trivial to show that this nulling condition corresponds to the case when the VDC is equal to the surface potential. So VDC is something that we control via the feedback. Surface potential is something that we want to measure. So the zero of the first harmonic of the force corresponds to the case when the VDC that we know is equal to the V surface that we want to measure, and therefore the map of the VDC gives us the map of the surface potential. So for the ideal feedback, signal is independent of the phase and amplitude of the response, and in the previous lecture we discussed the deviations from this behavior due to the feedback nonlinearity. In this lecture, however, we are going to look a little bit under the hood of the KPFM operation and kind of look at how it works and how to make it work better. So let's start with the most fundamental question of how does this selection of the first harmonic of the force practically works. So practically we have a piece of electronics called the lock-in amplifier, which basically acts as the notch filter. So what it does, it takes our detected signal, it mixes it with the excitation signal and integrates it over some time integral. So mathematically we can say that the output of the lock-in amplifier is an integral over some time of the excitation waveform times the measured signal. So in terms of the Fourier component, the lock-in amplifier works essentially as the notch filter. If our signal has some frequency spectrum, the lock-in amplifier selects only the part of the spectrum that is close to this resonant frequency. And the width of this peak is determined by this 1 over t time integral. So the longer we measure, the more narrow becomes the filter. So practically, more modern lock-in amplifiers are two-phase detectors. So we do this calculation twice, one time for the reference waveform, another time for the waveform shifted by 90 degrees. So it gives us both the in-phase and out-of-phase component of the response. Or if you will, we can always convert it into the amplitude and phase of the measured signal. So lock-in amplifier is an extremely powerful tool because it allows us to measure the small periodic signals if we know the driving force that induced the signal. So in principle, in some sense, you can say that lock-in amplifier enabled the scanning probe microscopies in general and Kelvin probe microscopy in particular. Now, Of course, there are some limitations of the lock-in amplifier. So first of all, it's a notch filter, so the information at all the other frequencies is lost. So good lock-in amplifier will allow you to measure the signal at second, third, and higher harmonics, but signal at, for example, harmonic 1.5 is going to be completely disappeared. Secondly, by design, lock-in amplifiers are going to ignore the transient and spurious signals. So if something happens in the system and it's not periodic or not related to our excitation, it's going to be lost. And third problem is that we always have a compromise between the bandwidth and the temporal resolution. So what I mean by that is that if we set this time constant of the lock-in amplifier to be very large, then we reject a lot of noise, but at the same time our measurements start to take a lot of time, and this time can become larger than we are willing to spend per pixel. At the same time, if we set the lock-in time constant to be very small, then the lock-in works very fast, but then our noise level in the measurement is very high. So practically, we always choose the lock-in amplifier time constant comparable to the pixel time during the image. That's kind of a compromise between the two. And if you want to kind of learn more about it, then the lectures on the PFM show in the detail the effect of the lock-in amplifier on the measurement. So here we are not going to go into that. Now, the second way we can detect signal in the KPFM is through so-called the phase lock loop, which impose the feedback on the resonant frequency. So the way it works is that it compares the signal to the excitation signal and tries to adjust the frequency so that phase shift is equal to 90 degrees. So phase lock loop is a more complex piece of electronics than lock-in amplifier, and basically what you want to know about it is that it allows us to maintain the circuit at the resonance, so finding the resonant frequency, rather than amplitude and phase. And you can learn more about both of those on the Wikipedia or any kind of introductory book on the electrical engineering. Now, these are the basic tools of the KPFM measurement. So lock-in detection for the amplitude detection and phase lock loop for the frequency detection. Now, let's look a little bit in the philosophy of the KPFM methods. So there is a large number of them, as I will illustrate in this lecture. The question is, how is the detection principle related to the physics that we want to explore? Let's start with the ideal case of the KPFM. So in this case, the force between the tip and surface is parabolic. The apex of this parabola gives us the surface potential. The curvature gives us the capacitance. So the vertical shift is actually irrelevant because this is just additional forces in the system. And what's important is that these forces are time independent. So in this case, in this ideal case, the system is characterized by two parameters, capacitance and potential, and KPFM measures only potential and kind of ignores the capacitance. So of interest is, of course, measuring the capacitance. It tells us what is the material below the tip. There are other cases. So for example, if the material is semiconductor, the forces can be non-parabolic because of the accumulation and the depletion effects below the tip. If we deal with the quantum system, then the forces would be strongly non-parabolic due to the tunneling and other interesting quantum electrostatic phenomena. Second thing is that the forces can be time dependent. So obviously the classical KPFM measurements, which measure only potential, are going to give some bogus information in those cases. To address these issues, so measure capacitance, measure forces which are not parabolic, and measure the forces that are time dependent, multiple research groups all over the world have developed a whole slew of the KPFM methods. And they can be classified in terms of the excitation, control signal, detection, and the spectroscopy modes. So excitation signal defines how do we excite our probe. and this can be the electrical excitation, just sending bias to the probe as in a classical KPFM. It can be mechanical or photothermal, so mechanical by the piezo at the cantilever base or by the photothermal excitation of the cantilever itself, or it can be some combination. The control signal can be either on the level of the DC bias, so we can either have it fixed, or we can have a feedback, like in classical KPFM, or we can sweep the VDC bias to basically enable the spectroscopy. The VAC signal can be either sinusoidal, as in classical KPFM, of either fixed frequency or changing frequency if you use the PLL detection, or it can be a band excitation signal. Now, the detection can be amplitude-based, so the lock-in detection, frequency-based if you use the phase lock loop, band excitation if you detect in the band of frequencies in parallel, or it can be a G-mode detection. So I'll talk about it in more detail, but basically the G-mode is based on the full information capture of signal from the detector. So the excitation and the detection form the engine of the KPFM method. So the sinusoidal excitation lock-in amplifier is the classical KPFM, sinusoidal excitation and the lock-in detection is the phase shift frequency modulation KPFM, band excitation is the band excitation KPFM. On top of this engine, we can impose the specific spectroscopic conditions. For example, we can measure the signal as the function of voltage applied before the measurements, or voltage applied during the measurements, or time. And I'll show you some examples of this type of spectroscopic measurements. But first, let's go through the specific combinations. So for single frequency KPFMs, there is a number of the possible excitations and detection modes. So this is the types of the technique: amplitude modulation KPFM, when our driving is electrical and our detection is using lock-in amplifier. We have the feedback. Our detection is based on the electrostatic force, and our measurement gives us the contact potential difference. We can have a dual harmonic KPFM, where the driving is still electrical. Detection can be lock-in or PLL. The interaction that we measure for electrostatic forces and force gradient. We don't have a feedback, but we measure the CPD plus capacitance. We can have the dynamic KPFM, so this is described here. We can have time-resolved KPFM and time-resolved EFM, which give us the information of the time dynamics. We have the other modes of the KPFM, which I'm going to go through in more detail. So notice that many of these techniques are not commercially available, so the commercial machines are sufficiently flexible to implement them, but most of the time you need to have a reasonably good idea of what exactly aspect of material physics or chemistry you want to look into that informs your choice and configuration of the KPFM mode. So historically, many of these modes were proposed and perfected by specific research groups. So for example, the dual pass AM KPFM was advanced strongly by the Jacobs group. The dual harmonic KPFM was explored by Collins and Takeuchi. Time resolved KPFM was explored by Strelkov, and for example, time resolved EFM was explored in detail by David Ginger group, and so on and so forth. So I'm giving the names of the techniques and the corresponding references, and as usual, you are more than welcome to explore this in a greater detail. In addition to the single frequency KPFM methods, we also have the multiple frequency KPFM, which include the multiple excitation signals, half harmonic band excitation signals, photothermal band excitations, and the intermodulation Kelvin probe microscopies, which are defined on this slide. And again, you can find the relative references for single pass AM KPFM, frequency modulation, half harmonic methods, band excitation, photothermal band excitation, and intermodulation in these references over here. But during this lecture, I'm going to talk about the logic behind the choice of specific techniques and how the different configuration of the KPFM setup allow us to measure some specific interactions. So let's start with the relatively simple example of the dual harmonic KPFM. So the idea here is that imagine that we excite the cantilever and tip with the periodic voltage. So in this case, we expect to have the response at the first harmonic due to the capacitive force, and this response will be proportional to the tip surface potential difference and the driving voltage acting on the cantilever. At the same time, the response acting on the second harmonic, so twice the excitation frequency, would be proportional by the same capacitance gradient and VAC square. So this is really a very simple algebra. The only difference here is that what we measure is, strictly speaking, not the force. What we measure is the response amplitude. And in order to transition from the force to the amplitude, we need to multiply our signal, our force signal, by the transfer function of the cantilever and divide by the spring constant. So if we were measuring the forces, it would be enough to divide the response at the first harmonic to the response of the second harmonic in order to get the tip surface potential difference. Practically, however, it doesn't work this way because we don't measure the forces, we measure only the something proportional to the force. So one way to avoid this problem is to calibrate the cantilever transfer function. So if we know the function g of omega, meaning that for each excitation frequency we know both the response at this frequency and the transfer function at double the frequency, then we can compensate for the transfer function and basically get the expression for the VCPD directly by dividing the response at the second harmonic with the response at the first harmonic. So this approach was proposed by the Japanese group, and it actually works remarkably well. Question is, can we do it close to the resonance? And the answer is not really, because close to the resonance, transfer function of the cantilever starts to change. At the same time, measurements close to the resonance are of interest because this is where we can use the amplification factor of the cantilever. So the response is amplified by the factor of Q compared to the response away from the resonance. Question is, how can we do that? And one approach to do that is through the use of so-called the band excitation mode proposed by Stephen Jesse and myself about 14 years ago. So the idea here is the following. Imagine that we have a classical AFM where we excite the system using the sinusoidal signal and we detect the sinusoidal signal. So for the lock-in detection, we detect the amplitude and phase. In the Fourier domain, this essentially corresponds to just a single frequency. And once we have a single frequency, the information on the response of other frequencies or the changes on the resonant transfer function of the cantilever is lost. So the idea of the band excitation methods was to substitute the excitation of a single frequency by the excitation at the band of frequencies. So now we start in the Fourier domain and have a signal which has some band of frequencies, for example, uniform amplitude. We do the inverse Fourier transform. We send the signal to the cantilever. We detect the response. We find the response in the frequency domain, and the ratio gives us the transfer function of the cantilever. So it turns out that there are a lot of things you can do with this band excitation approach signal. So there are ways we can shape it, for example, using the different functional forms. So sinc, sinus signal divided by time, has a uniform phase in some band, and this is how it looks in the time domain. And chirp signal has a form like this, and it's also uniform in the frequency domain, but the phase content is more complicated. And this is how the chirp looks in the time domain. And it turns out that there is a very a large number of signals between the sync and the chirp limit, which corresponds to different relative dephasing of the parallel frequencies. So there are a lot of ways how we can play with the band excitation signal to make it tuned for specific application, but kind of this is something that is a second or third level detail for this particular discussion. Now, the important thing is that once we have the band excitation signal, we can use it to run the KPFM. And there are multiple ways to configure the band excitation detection of the KPFM. So for example, we can have the open loop measurements. So in the open loop measurements, we use the sweep of the DC signal and measure the response as the function of the DC. We can simply substitute the sinusoidal wave by the band excitation and have the feedback on the band excitation signal. Or we can use the band excitation signal in the half harmonic configuration. And we are going to go through some of these examples in the next slides. Let's start with the example of the open loop band excitation KPFM or OLB KPFM. So here what we do is that at each spatial point, so that for each tip position, we apply the multiple VDC levels to the cantilever. So we do measurements when the tip bias is -8 volt, -7 volt, -6 volts, and so on. We send the band excitation pulse to the tip. We measure the response. So in this case, for each point, we measure a signal like this. So the horizontal axis here is the bias, the vertical axis here is the frequency, and the picture what you that you see is the response of the cantilever to the modulation as the function of bias and frequency. So what you can see here is the peak. This is the cantilever resonance. And the interesting thing is that if you look at this data very carefully, you can see that the position of the peak actually shifts with the bias. And that makes a lot of sense because we know that in the Kelvin probe measurements, both the resonance frequency changes as the function of the tip surface interaction and the amplitude changes. So the amplitude changes because of the capacitive force and the frequency changes because of the force gradient effect. This is what is used in the frequency detection KPFM. So in this case, we measure both of these interactions at the same time. And what we can do is to take this data set at each pixel and extract the bias dependence on the amplitude and the resonance frequency and the Q factor. So from the bias dependent on frequency, we get the nulling bias, which is the surface potential. So this is just a parabola. But interestingly, we also get it from the amplitude. So in some sense, we measure surface potential in a way that combines both the amplitude-based KPFM and the frequency-based KPFM, exactly because we measure amplitude and frequency at the same time. And this approach allows the full compensation for any kind of crosstalk, for example, the resonance frequency shifts. The problem, of course, becomes that the signal is weak close to the nulling bias, so we sort of have to extrapolate the measurements away from nulling bias close to the nulling bias. And this is the example of how the open loop band excitation KPFM works. So this is a region formed by the silicon and gold. So this is a gold electrode on silicon. We use the AFM tip to write a charged region. So this is a deposited charge on the surface, and then the classical KPFM image, we will see the difference in the work function between gold and silicon, and we also see this deposited charge. So this is these two images are classical pair of the surface topography and the KPFM image. And these four images tell us the information from the OLB KPFM perspective. So this image tells us the opening of the parabola. And what you see in this case is basically the difference in the electrostatic properties between the silicon and gold. And you see a very characteristic wave in the capacitance close to the step edge. So this is a topographic crosstalk that appear simply because on the step edges the capacitance changes. So when we come close to the edge from this direction, the capacitance drops because there is a drop of the surface. But once the tip moves down the edge, then it starts to interact both with the material and the edge itself, so the capacitance goes up. So this characteristic drop down, drop up of capacitance on topographic inhomogeneities is the kind of intrinsic crosstalk of the capacitive sensitive KPFM methods. At the same time, we can get a nice picture of the surface potential, and we also get a picture of the resonant frequency shift, and we get a picture of the Q factor. So for the resonant frequency shift, you can see that there is some difference between the charged and non-charged region. And for the Q factor, there is something interesting going on inside the charged region as well. So all of a sudden, instead of having just one parameter, effective potential, we have 4 parameters that tells us something about the tip surface interactions, local capacitance, and local losses. You can ask a question, why is that we don't use this method to study this material system in more detail? And the answer is, of course, we can, but as I pointed in the previous lecture on the ferroelectrics and the grain boundary systems, for ambient KPFM measurements, the surface is covered by the water layers, and many of the signals we measure, even on the quantitative levels, would be related to the property of these water layers, meaning that it requires a much more involved and detailed study, but you cannot just say that this is the property of the silicon. What you measure would be a property of the water layer of silicon, which is interesting but need to be studied in more detail. Okay, a second example of the band excitation based KPFM measurements is the half harmonic band excitation. And here the idea is the following. So again, at each spatial point for fixed tip DC bias, so we no longer sweep it as was the case for the open loop KPFM, we have it fixed. We measure the response to the band excitation pulse, which is centered at the resonant frequency of the sample. And at the same time, after this measurement, we configure a different signal which is centered at half the resonant frequency. We excite at this half resonant frequency, but we measure the response at the band centered at the resonance. So in some sense, we measure the second harmonic of the response. So basically, we measure the response at the resonance twice. One time, the first harmonic response when we excite and detect at the same frequency, and the second time when we excite at half the frequency, but we detected this frequency. So in this case, we measure the first harmonic of the force. In this case, we capture the second harmonic of the force. And the elegance here is that we no longer need to worry about the calibration of the transfer function of the cantilever, because we detected the same mechanical conditions. So this allows for the full compensation of the indirect crosstalk and transfer function. Of course, it is sensitive to the choice of the DC bias, and here is the example. So this is the same gold silicon system when we try to do the measurements using the half harmonic BE KPFM, and you can see that we can measure the surface potential and the resonant frequency shift. However, we start to see that for the large biases, our applied bias start to affect the resonant frequency and they start to affect the Q factor. And we don't know exactly why, but we can clearly see that the quantitative measurements are possible only close to the zero bias. Of course, it's tempting to compare the numbers. So which of those Kelvin probe measurements is more quantitative or more reliable? So this is the example when we look at the flake of the graphene grown on the copper surface. So we all know that graphene and layered materials are magical, but it turns out that they're also useful for calibration of the scanning probe microscopy techniques. And what we do here is we measure quantitatively the contact potential difference on copper and graphene using classical KPFM, using the dual harmonic single frequency KPFM, and dual harmonic band excitation KPFM. And it turns out that the single frequency and BE version give almost identical values for the CPDs, so both for copper and graphene. And classical KPFM gives a pretty large systematic error, so the values for the CPD are considerably shifted. So this shift happens because of the feedback effect. At the same time, the contrast between the gold and copper and graphene is the same for all three techniques. So what does it mean? So KPFM is the classical techniques, it's commercially available, it's easy to implement, but it suffers from the systematic error due to the feedback. DH KPFM requires the classical lock-in detection, but it requires a very careful and meticulous calibration of the transfer function. The band excitation version does not require the calibration of the transfer function, but slightly longer. But in terms of the numbers, both techniques give almost identical answers for well-characterized system. So we can trust all of them, except for the classical KPFM, where we need to compensate for the feedback appearance. Now, it turns out that we can configure the KPFM in a different way. And in this different way, rather than exciting the cantilever electrically, we can excite it mechanically. So the reason why we want to do it is because by the nature of the electrostatic interactions, the force is small when our tip bias is close to the surface bias. At the same time, if we use the large DC biases, then we start to have the nonlinear interactions because of the additional electrostatic forces, cantilever position changes, nonlinear screening, and so on and so forth. In comparison, if we use the photothermal excitation, then our excitation force is constant and does not depend on the proximity to the nulling potential. And this is the example of this photothermal band excitation KPFM. So here we do the DC bias, we do the photothermal excitation, and we measure the frequency and amplitude of the cantilever oscillation as a function of the DC bias. So for the electrical excitation, we have a classical V shape for the amplitude and parabola for the resonant frequency. For the photothermal excitation, we have a constant excitation, it doesn't depend on the DC bias, and we have a perfect parabola for the resonant frequency shift. So this approach works remarkably well, and this is the comparison of the classical same samples. So we have silicon and gold. We have the classical KPFM image, so again we deposited some charge here and it kind of diffused. We have a photothermal image. In this case, we measure the signal with the higher localization because we measure the force gradient rather than forces, so there is a higher resolution. And in addition, we also get the detection of the capacitance, so we can clearly measure the capacitance difference between the gold and the. Now, if you're interested in this techniques, so this is a list of papers where they explored. So primarily it was the work of Saint-Leger, who worked on the open loop BE and half harmonic BE, and Liam Collins, who is currently at Oak Ridge, who worked on the open loop and the dual harmonic KPFM methods and the extensions for the three-dimensional multi-frequency methods. This is several more papers where this approach is applied for different form of measurements and ultra-fast KPFM applications. Now, let's talk a little bit about the force volume measurement. So if we have a AFM and we can configure it to any form of detection, we can measure the forces both as a function of force of lateral position, and also the function of distance. And this allows us to configure the microscope in one of these BE modes to measure the surface potential as a function of tip surface separation. And in this case, we kind of get this type of three-dimensional pictures, which shows us how the surface potential evolves as a function of distance from the surface. So you can get a three-dimensional picture of the force volume above the material, which tells us how the force decays away from the surface and allows us to extrapolate to the surface. Now, what about the spectroscopies in KPFM? So when I talk about the KPFM measurements before, I talk purely about the detection mechanism. So we assume that the surface have some static properties which are characterized by the CPD or some form of deposited charge. It has some capacitance. And we talk about the different ways we can configure the microscope to measure those capacitances and surface potentials. What about the spectroscopy? So what I mean by that is, imagine that I want to know the properties of the surface not in static condition, but after it was pulled by the tip at a given bias. For example, imagine that I take the surface and try to polarize it with the tip of the bias of 10 volts. And then I want to measure the surface potential. Then I want to take the same surface and try to polarize it with the tip with the potential of 9 volts and take the surface potential. And so on and so forth. So in other words, I want to measure how induced surface potential depends on the bias applied prior to measurements. Obviously, this measurement is a little bit difficult for the very simple reason that once I induce the potential on the surface, then the potential on the surface is no longer the same. So I kind of cannot really compare the response of the same part of the surface. However, I can run a very simple model of these measurements when I assume that for some specific material, the surface properties are uniform. And then rather than measuring one region many times, I can measure multiple regions one time. And this is the example of these measurements when I have a surface of the titanium dioxide. I bias it with the tip with the different biases, so minus 13 volts, minus 10 volts, minus 7 volts, all the way to plus 13 volts. And then I measure the induced potential on the surface as a function of the potential of the tip. So what is interesting is that if I plot this behavior for, say, two samples, A and B, I can see that they form a universal curve. So for some voltages, I start to change the surface potential, but for very strong positive voltages and very strong negative voltages, the surface potential actually saturates. So meaning that if I try to bias the surface with a tip at minus 10 volts and minus 15 volts and minus 20 volts, then the surface potential after this biasing will not be minus 10 and minus 15. It would be sort of minus half a volt. Same thing for the positive direction. So for positive and biasing at 10 volts and 15 volts, my surface potential would be close to zero. So why does it happen? It happens because the surface of the dielectric can be charged, but the degree to which it can be charged depends on the transport properties of the surface. So if you apply too strong a bias, then the transport mechanism due to the ion diffusion or semiconducting transport become activated, and the surface cannot support this potential anymore. So the charge start to move away. And this is the phenomenon of the constant contact charging that is related to the redox density of states on the surface, or semiconductor density of states, depending on whether this is a chemical or physical process. But the important thing is that we can measure it with the KPFM. And in fact, we can even configure this experiment when we try to find out whether the strong polling, for example, I poll the surface by the very strong negative bias, say minus 15 volts, would it affect this curve? And it turns out it does. So if I compare the contact potential difference for the pre-polled negatively and pre-polled positively surface, I start to see the hysteresis. Not a very wide hysteresis, but noticeable hysteresis. So the problem with this approach is that it's very easy to run. This is just a standard KPFM measurement. But in this case, we measure the properties of the surfaces on average. So we don't measure the response of the local surface element. So in order to access this type of behavior, our group have introduced the concept of the contact Kelvin Probe Microscopy, CKPFM. So the idea here is that we both measure the electrostatic interactions and poll the surface during the same measurement. So the bias applied to the probe is the sequence of the write and read pulses. So we apply the bias like this. This is a bias that sets surface potential. And then we read out the response using the open loop version of the KPFM on contact. Then we apply a larger write bias, and then we read it again, and then we continue it for the multiple writing biases. Different way to configure these measurements. Turns out that we can do something very similar if we have this measurement sequence of the writing and reading biases, but rather than having the open loop version, we will have a constant read bias with a superimposed sinusoidal wave. So this is kind of a technical tweak on the detail. And it turns out that this approach works remarkably well. So this is the example of the charge pattern in hafnium dioxide. So this is a material which may or may not be ferroelectric in the films due to the strain effects, but it turns out that the surfaces of this material without electrodes behave like an electret. So they can maintain charge, but they doesn't seem to have the ferroelectric type dipole. So what we can do is to write the pattern using the charge tip, and then we can read out this pattern using the classical Kelvin probe microscopy or using this contact KPFM. And it turns out that KPFM gives us this type of behavior, and CKPFM gives us a much higher potential, so that the resolution in CKPFM and contact mode is much higher. The problem, of course, is that when we keep reading out the potential using classical non-contact KPFM, the potential pretty much doesn't change with time. So it is fixed, and it doesn't change much because when we do the readout, our tip doesn't touch the surface. If we try to do these measurements with the CKPFM, you can see that we measure strong contrast during the first scan, and then the contrast disappears. And this happens because in the CKPFM, the readout is destructive. We basically zero out the surface state. So this is a spectroscopy that allows us to measure surface charging, and the charges can be exchanged between the tip and the surface. We gain very high spatial resolution. We lose, our charges are not standard. In the KPFM, the charges cannot be exchanged with the tip during the measurement state, so they stay in place, but the resolution is much lower because now we measure the electrostatic forces away from the surface. So it turns out that CKPFM on the dielectric surfaces give us a very rich spectrum of information on the surface charges and surface electrochemical behavior. So we can study the phenomena such as the hysteresis of the junction potential. We can study the evolution of the electrostatic forces. We can study the time dynamics. And many of these areas are still open for exploration. So for the time being, our effort has been focused on exploring ferroelectric materials for CKPFM, in which case we detect primarily the ferroelectric loops. But as I said, this is the area which is can be of extreme interest for the classical ferroelectric and non-ferroelectric materials, oxide, semiconductors, solar cells, and so on and so forth. So if you are interested, you can find more information about the CKPFM and the following publications. So starting from Nina Balke's paper of 2014 and continuing to the 2015 and the recent review paper that illustrate the CKPFM applications for ferroelectrics. Now, let's talk about the transition from the band excitation to the G-Mode scanning probe microscopies. So G-Mode SPM is rather unusual and novel technique. So let's first talk about the general principle of the G-Mode and what it is in the first place. So in the very beginning of this lecture, I illustrated the application of the lock-in amplifier for the detection in KPFM. And the lock-in amplifier is used in the same way for all amplitude sensitive SPM techniques. So generally we apply some form of excitation, for example, sine wave. We detect the response, which is going to have the first harmonic component, and then we use the local amplifier to select the amplitude and phase only at this first harmonic. So the G-mode approach utilizes a slightly different concept. So rather than detecting the response only after the local amplifier, what if we just store and then post-process all the signal detected by a photodiode? So notice that the band excitation is, strictly speaking, parallelization of lock-in. So we excite by multiple frequencies and we detect by multiple frequencies. G-mode is slightly different idea. So we can excite by sine wave and we can excite by the band excitation, or we can excite by any other signal, whether it is spread spectrum modulation or what's not. The idea of the G-mode is that rather than process and store process signal, we store the whole signal. And it turns out that this approach allows us to do a rather interesting thing from the perspective of understanding how the SPM works and from the type of measurements we can do in SPM. So let's look at the example. Imagine that we have a cantilever which starts to interact with the surface. And the cantilever never responds to the surface instantly. So first we have some transient behavior, and then this interaction becomes stationary. So the important thing is that if we detect the full signal, we get a lot of options that we never can get with the lock-in. So lock-in will just average all this behavior down to one number. But if we store the full signal, then we can start to play with the way we represent it. For example, if we're in the stationary region, we can start to play with the spatial resolution. For example, we can take the same sequence of response and divide it in some number of the spatial pixels, or we can divide it in 4 times larger number of spatial pixels or 16 times larger number of spatial pixels. So we have a controllable resolution. And of course, if we divide the time trace in more parts, then our noise level goes up. But as you can see, that's not a very significant effect. These are a few examples of application of the G-mode to the classical SPM signals. So this is a sort of surface phase separated polymer. So you have two polymer phases and you can look at them in the error signal, and you don't see much here. This is the example of the same system imaged by the G-mode. So we excite the tip in a sinusoidal fashion, but rather than storing the response only at the first harmonic, we store the full response. Then we can do the Fourier transform and we get a data cube which gives us the full harmonic of response as a function of for each position. So we can visualize it when we show the amplitude and phase of responses at all frequencies present in the system. Some of these frequencies, or one of these frequencies, is the frequency at which we excited. But many of these frequencies correspond to its harmonic or some spurious responses around the cantilever resonances. And it turns out that we can have a beautiful images even at the frequencies at which we did not excite the system. So look at it one more time. So this is how our amplitude and phase look at the function of frequency, and we sweep through this frequency space already after the measurements. Of course, the problem with this type of approach is that we never know what is the right frequency, right? So we have beautiful images, but they all look differently, but which one is the right? So it turns out that if we want to work with this type of data cubes, there are very powerful techniques coming from the big data and information theory domains. So now there are multiple groups that start to apply big data methods in the microscopy, both SPM and electron microscopy. A few years ago that was rather unusual, but nonetheless this works remarkably well. So for example, we can take our data cube, the signal versus frequency, and we can do the so-called principal component analysis. So we divide it in the statistically ordered loading maps and the eigenvectors. So the first eigenvector looks like this. This is just the full signal of the cantilever. The second start to look like this. The third and fourth start to show the reverberations of rather characteristic shapes. And these are the loading maps which show the evolution of properties corresponding to these eigenvectors. And you can see that, for example, the first eigenvector is just the topography. The second eigenvector shows a very rich structural information inside the polymer matrix. So if you look at it, you can see a very precise structure of these crystallites inside the polymer. The third and fourth loading maps actually show the transient due to the tip surface interactions and topographic features and so on. And in fact, we can check the information content in these images by looking at this eigenvectors versus the frequency. And you can see that in the tapping mode measurements, the information is actually concentrated in a pretty large number of this eigenvector, so of order of several hundreds. And that basically means that the interaction between the tip and surface are strongly nonlinear. What was very interesting is that if you work with this information theory methods with the scanning probe microscopy data, you start to develop a very good feeling of which scanning probe microscopy methods are robust and which are not robust. So, for example, for techniques like PFM, if you tune it right, you always get roughly the same answer. At the same time, if you look at the phase image in the tapping mode AFM, the image would be very sensitive to the detailed tuning of the microscope. And it turns out that this behavior is very well reflected in the G-mode. So if the technique has 2 or 3 relevant loadings and eigenvectors, this technique is robust. If there are 100, this technique would be very sensitive to the experimental parameters. But anyway, we can explore the information distribution of these eigenvectors. So it turns out that not all of them contain interesting information about the spatial features. So it turns out that some of them are dominated by some form of noises. So, for example, it will filter out the 60-cycle noise. Some of them, however, are strongly related to have strong spatial variability, and therefore it basically offers us a way to denoise the signals. For example, we can take the eigenvector and loading maps that contain spatial information and throw away everything else. So there are a lot of ways you can do with this, much like you can do a lot with the classical TV and the video compression scheme. Nonetheless, we have this G-mode method. We can apply it to tapping mode. We can apply it to the magnetic force microscopy. We can apply it to PFM. So this is an example of the imaging of the yttrium iron garnet in the classical MFM and the G-mode MFM. So we can see a rather beautiful signal. And we get a lot of additional information by exploring the loading maps and seeing the details of the ferromagnetic domains and corresponding response frequencies. And it turns out that even in senior components, we can sometimes start to see the transient behaviors when the tip crosses the domain wall. So it gives rather beautiful patterns and also very easy to identify based on the maps. And it also turns out that this approach allows us to denoise the signal very effectively. So certain forms of noise get channeled to specific components, and therefore they're very easy to remove after. So this is one more example of the high order G-mode MFM. Anyway, this technique works remarkably well, and you can read more about it in the original paper by Alex Belyaninov and Liam. The question is, how can we apply this G-mode principle to the KPFM? And the idea is very simple. Rather than driving the piezo or mechanical piezo, we apply the bias directly to the cantilever. And unlike classical KPFM, we are going to capture the full signal flowing from the detector. So what happens in this case? So this is the typical example of the response spectrum of the cantilever as a function of frequency. So what you can see here is the noise floor on the system. So this is just the noise of all the electronics and a measurement component. And you see here the peak corresponding the driving frequency, which we choose to be close to the first resonance. You start to see the harmonics of this frequency. Notice that this is a logarithm of response, so this response to this harmonics is much weaker, but nonetheless it's not zero. So interactions between the tip and the surface are always nonlinear. In most measurements, this nonlinearity is very weak, and practically we can say that it is irrelevant. But practically, if we can measure it, then we can already work with it. And also you can see here the peaks corresponding to the first, second, and third eigenmode of the cantilever. And these peaks are due to the thermal excitation. So the thermal noise will excite the cantilever, and this excitation depends on how close we are to the resonance. What's also interesting is that you can just see by eye that the intensity of the harmonics of the signal actually depend on the proximity to the second and third resonance. So this is a standard effect that the response in the AFM is determined by the driving force multiplied by the transfer function of the cantilever, and the transfer function has peaks around the eigenfrequency. So what are we going to do with this? So we need to start with the response as a function of frequency. We need to apply the low pass filter. So we really need to know the first and second harmonic. We, in these measurements, are not interested in anything else. We are going to denoise the signal. And after we do that, this is what happens. So here the gray curve shows the raw data, and the red curve shows the process and denoise data. And what's interesting is that you can see that there is a response at both the first and second frequency of the signal. And after the data is denoised, there are quite a lot of things we can do with it. So one thing is that we can always reduce the problem to the one which is already solved. So we have the signal at the first harmonic, we have the signal at the second harmonic. We can use the approach similar to the dual harmonic KPFM in order to get the amplitude and phase of the response and then the classical KPFM signal. But we can do more elegant things. For example, if we have the full trajectory of the cantilever, we no longer have to get the first and second harmonic. We can simply reconstruct the force acting on the cantilever and directly reconstruct this parabolic force, parabolic tip surface force. And then finding the surface potential becomes trivial. Or we can use the same information theory analysis based on the principal component analysis and more complex techniques to separate the measured signal into relevant components. And let me illustrate several examples of this KPFM, G-KPFM application. So let's start with the simple emulating the lock-in. So this is the example of the two lines, crossing gold and platinum line on silicon, where we measure them by topographic signal. We measure the full G-KPFM signal over it, and then for each pixel we can reconstruct the full response as a function of bias. So this is an open loop measurement, and frequency. And you can see that the static component is independent on bias. That's fine. The omega component shows the classical first harmonic response shape. Second harmonic component does not depend on the bias, as it shouldn't. And we also have a peak corresponding to the first eigen frequency of the cantilever. So this is a thermal peak. And again, we measure this type of signal at each spatial pixel, and from it we can reconstruct the amplitude and of the first and second harmonic response. We can reconstruct the CPD, and by the nature of the G-mode, we can represent the data with the different number of the spatial pixels. So we have a tunable resolution in the fast scan axis direction. Construct the force voltage curve at each point, just out of the observation of the trajectory. So what we do in this case is that we have the cantilever transfer function, we have the measured signal, or we reconstruct the signal into the Fourier domain and then transfer it back to the time domain, and then we plot the force acting on the tip or cantilever displacement as a function of the bias applied to the probe. So in this case, we basically assume that the transfer function is constant, meaning that we do it well below the first resonance. So in this case, the measurement would be rather straightforward. And this is rather an interesting step forward, because rather than having the classical KPFM approach of finding the nulling potential, we just reconstruct the force voltage curve at each special pixel. And once we do that, it is relatively trivial to take this force voltage curve, fit it by parabola, and we can plot the coefficients of this parabola. So we plot the first coefficient, we plot the second coefficient, and we plot the position of the apex. So the position of the apex gives us the CPD. So this is just a surface bias. The opening, the second quadratic component, gives us the capacitance, and we see this classical picture of the positive negative feature of the step edges. This is just a topographic crosstalk. And the vertical offset gives us also something that we don't quite understand. So what it tells us is that by using this reconstruction of the parabolic force, we can run the KPFM measurements much faster than the classical KPFM, because in this case we don't have to average the signal over multiple oscillations to do the lock-in, and we don't have to wait until our feedback works. We can just take several oscillations of the cantilever and reconstruct the parabola out of it. So this is acceleration by about a factor of 1,000, and I'll talk more about it later. So another way we can analyze the signal is by taking this force voltage signal and using the principal component analysis. So in this case, it turns out that the principal components from 1 to 5 look like shown on this slide. So the first one is just an average signal, so it basically represents the elements of the microscope drift. The second and the fourth one are effectively transients, which are random in nature. You can compare how the eigenvalue and the loading map look like. But the third and fifth component gives us essentially the CPD, the lateral shift of the parabolas, and the capacitance, the opening and closing of the parabolas. So it also tells us that there is some additional information in the KPFM even on the nearly ideal surface. And it also tells us that in the stationary case, the lock-in detection is complete. So we come up with a very information-rich version of the scanning probe techniques, and we compared it to the classical one, and we basically understand why the classical KPFM works so well. Because in the stationary case, it's complete. Of course, that was a trivial answer. We can get a very easy experiment when we actually do need the G-Mode KPFM. And this is the case where we have a metal electrode next to silicon oxide. And what the metal electrode does, it injects the charges inside silicon oxide. So this process is actually pretty fast. It's very difficult to map it using the classical KPFM, but the GKPFM gives us the advantage of the fast response. So we can do measurements on the millisecond time scale, where the classical KPFM operates at the second time scale. So we do get a fast measurements as the outcome. Not that fast, we are still at the milliseconds and not microseconds, but let's see what else we can do. Now, how can we drive the detection further? And one of the obvious approaches in the excitation and detection is that I mentioned that with the G-Mode, we detect at all the frequencies, but we excite only at one frequency. So what will happen if we excite all frequencies sequentially and detect at all frequencies for all frequencies? Then we get what we call omega squared method, when we measure the response of the system at all frequencies while sweeping the excitation frequency. So it turns out that this measurement is actually pushing the technical capabilities of modern microscope from the point of view of the information infrastructure. So we see a picture that makes a lot of sense. So we see resonances in the system. However, it takes about an hour to get the data for 40 by 40 pixel image. And the problem is that we get about a gigabyte for pixel. So in this particular case, it was about 1.5 terabyte of data. So it's these experiments required supercomputer principal component analysis. But for the time being, this is a tour de force experiment. We know that we can do it. It works. It gives us something interesting, but until our capability to work with the terabyte volumes of data catches up with our experimental capabilities, we are probably not going to push it further. Now, what can we push? We can push the time resolution on KPFM. And the reason why we want to do that is that in many material systems, it is the time responses that are ultimately interesting. And the problem is, why can we not measure it in the usual KPFM measurement? The answer is because of the cantilever ringing. So if our force pulse applied to the tip looks like this, our response of the cantilever looks like this. So after each full force pulse, the cantilever starts to oscillate at its eigenfrequency, and it keeps ringing on the time scale determined by the Q factor. And this cantilever ring down time is understood extremely well as a function of the resonant frequency and the Q factor, and you can find this information in this paper by Adams and co-authors. So can we somehow get around this time limit because of ringing? And it turns out that we can do it using the approach called the fast free force reconstruction, or F-cube-R. And the idea here is very straightforward. So cantilever is the dynamic system, meaning that the response of the cantilever to the force is the product of in the Fourier space, is the product of the force with the transfer function of the cantilever. So strictly speaking, if we want to measure the unknown force, we need to know the transfer function, and this transfer function can be position dependent. So if we have a cantilever strongly interacting with the surface, then the transfer function changes, so the system is no longer linear. However, in the KPFM and some other techniques such as the EFM, the transfer function in the first approximation is constant, which means that we can calibrate it one time before the experiment and then assume that this transfer function is constant, and it can be treated as a known variable. And then what we can do is to measure this transfer function, measure the displacement signal, Fourier transform it, deconvolute the transfer function, and then recover the force acting on the cantilever. So notice that when I showed you the example of the fast G-Mode KPFM, that method was relying on the fact that our transfer function is constant, meaning that we are far from the resonance. In this case, meaning constant means doesn't depend on frequency. In this case, we assume that the transfer function depends on frequency, just is the same for different spatial locations, so it can be calibrated. And this allows us to do measurements at the first resonance and higher resonances, and this is how it works. So this is the example of the measurement of cantilever displacement when we have our cantilever parked above the metal electrode. This is the electrostatic force we apply to the electrode. This is the raw response of the cantilever, so we operate very fast. And this is the response which is obtained by the transfer function compensation. So you can see that this was a perfect square wave, or at least we think it was a perfect square wave. And this is the response, which looks like almost like a perfect square wave, and our time resolution is now about 60 microseconds. So we went from millisecond regime to the mid-microsecond regime. Can we explore it systematically? Yes, we can. So this is the example of the measurement when we sweep the frequency of the excitation driving force. So we start with the square wave, but we make it faster, 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 faster. We measure the response of the cantilever, and you can see rather beautifully that for very slow frequencies, you see how the response kind of change like jumps, and then there is a ring down. And then when you accelerate it, the distance between the jumps becomes so small that you start to see almost the sinusoidal response of the cantilever itself. And this is what happens if we try to do the reconstruction. So this is the reconstructed force on the time scale of milliseconds. So we have a perfect reconstruction. And this is going to the smaller time intervals, and we start to see that the problems in tracing. So this is the time of the sweep, not the time of the segment. So here you can see that we're now operating on this microsecond region. So compare 1105 and 11.1. Now, if we want to define mathematically the time resolution and the information limit, we can use exactly the same trick as we did before for the spatial resolution and the PFM and the KPFM. So with the time resolution is defined as the time above which the quantitative force reconstruction is impossible. So we use a very conservative definition for it, that the recovered force drops below 95th percentile of the true force. And the information limit is the time beyond which not even qualitative detection is possible. So it turns out that in this particular measurement, our ring down time is about 2 milliseconds. So this is the lower boundary of the time resolution in the classical KPFM methods, and practically it's even worse than that because of the additional electronics. But in the FQ-bar methods, we can easily get to the 5 microsecond level, and this is only operating close to the first resonance. So practically we can also operate on the higher resonances and push the time resolution and information limit further. So with this technique in hand, we can actually start to work on this ultra-fast KPFM when we implement this FQ-bar method on real materials. And this is the example of the ultra-fast KPFM as applied to the gold electrode on this hybrid perovskite, when we basically apply light illumination and we see how the surface photovoltage responds to the light pulses on the gold electrode and on the material, and we see how the carrier dynamics induced by these measurements precedes the function of the time on the microsecond. So you can learn more about these techniques and these references. Notice that these are already very recent, so this field is actively being developed now. And thank you for your attention. And this is just a short summary of what is the variety of the available Kelvin probe microscopy techniques.